We are live. Nice. It's very bright. Alrighty. Should be a very exciting day talking about Lagrange's theorem, hopefully. Okay. Good morning. How's it going? Oh, hey. I enjoy those memes. Don't you? So that new Hearthstone expansion came out yesterday, and it is just pure cancer. It is the worst. 90%, literally, not actually exaggerating, 90% of the people are playing one class out of 10. It is the least fun day one of an expansion I've ever seen. But other than that, things are great. All right. I'm gonna go get tan on my run this afternoon. It's gonna be lovely. It's probably not actually gonna happen because I'm not physically capable of tanning, but you know, one can dream. I can hear you. Nice. Alright, we'll give it another minute or so here. Hopefully more people will show up. I feel like punctuality is somewhat gone by the wayside with Twitch streams. Okay, so just a reminder, if you're doing test correction stuff, if you are able to do oral corrections and want to do those, then you should talk to me and we should schedule something. Otherwise, you can just resubmit those over your test. Like, that should still be open. It'll just like show up as late. Maybe I'll make a new one. I'll just make a new thing that I'll do after class. So, test corrections by end of the day Friday. And you also have that brief reflection thing. Again, that should be fairly quick. Hopefully, writing about yourself is not too challenging, and the reading should take like no more than 5 minutes, I imagine. At least for like your first read through. If you want to soak it in and reflect, then maybe it takes a little bit longer. But it's pretty short reading. And then, you know, we'll get another problem set assigned here soon, but you guys had enough this week that that'll be due the following week. So obviously assigning it today for Friday would be a bit harsh anyway. Okay, so any questions on stuff before we get started? So I saw some people were kind of reworking through the cosets for the quaternions and seem to be looking better. I think once you realize what you're doing, it's not that hard, right? I mean, you're just doing multiplication in your group. So hopefully that doesn't feel too bad. And then today we'll get a little bit deeper into why we care about cosets, and hopefully we'll be able to prove Lagrange's theorem today. Should be able to. So any questions? Logistical or conceptual? Okay. Alrighty then. So let's maybe talk about one part from 5.4 just to make sure we feel good about this. So, we had Q8 as our group, and let's look at the subgroup generated by I. So how many, we'll talk about left cosets, maybe we'll talk about right as well. So how many left cosets did you find, distinct ones? Because obviously you have 8 elements in your group, but maybe some of them had repeats. How many cosets did you find? Please type a number in chat. All right, off to a great start. There we go. Yeah, 2. Yep, 2 is reasonable. Was there any difference between left and right? Did you notice left were different than right, same as right? What do you think? So I agree, we had 2 cosets. Thoughts? Yeah, so they were the same. So we get 2 cosets, distinct ones, and left are equal to the right. And so let's just kind of briefly look at this. So I has our 4 elements, right? We get 1, I, minus 1, minus I. And so again, for any element that is in this subgroup, just due to closure, you're going to get that thing back with the coset, right? So 1 times I is equal to I times I is equal to negative 1 is equal to negative I. These guys are all equal to I itself, right? And then if you look at any of the other elements, right, so let's just look at J, for instance. So this would give us J, Ji, which is negative K, negative J, and then negative Ji, which is K. And so you get plus or minus J, plus or minus K, and then this happens to be equal to negative J times I and plus or minus K times I. Right, so we basically get the stuff with I, and then we get our J and K ones as the other coset. And again, it doesn't matter if you do the left or the right in this case, they are going to be the same, right? Okay, so that is nice to see. We talked a little about 5, 5 last time with A4, and we saw kind of a similar thing, right? That if you have something that comprises like half of your group, that it seems like it doesn't matter if you do the left or right. And like I said, we'll talk about that later. That is actually always true. So then 5, 6. So here we're inside Z8. And this should have been the first time you kind of recognize what's going on with abelian groups. So I noticed all of you guys pretty much saw that pattern, that the order definitely isn't going to matter here. But I think this is a useful example because you have different notation. So what's our operation here? It's addition, right? This is an additive group. So we don't write, so here my subgroup was the subgroup generated by 4, which is just 0 and 4. So we do not write like 3 times 4 because that kind of implies multiplication, right? So don't do this. You would write 3 plus 4 for abelian groups, or, well, not necessarily all abelian groups. You can do that, but especially if you know like your operation is addition, then you should write it like this. Okay, so this is our notation for additive groups. Additive. And so here, again, thinking about Lagrange's theorem, we should end up with, this has 2 elements, this has 8 elements. We should expect to have 4 cosets that each have 2 elements, right? And so, if you start doing it, well, 0 plus h is going to be the same thing, obviously, and if you do 4 plus h, again, that's just by closure. These are going to be the same. And then you're just looking at like what happens with modular arithmetic, right? So 1 plus h, you get 1 and 5, but of course 5 plus 4 is 9, which is also 1 in here, and so this is also 5 plus h. 2 plus h is equal to 6 plus h, and then 3 plus h is equal to 7 plus h. Right, and that just takes a little bit of verification. And we know that left equal right here, since Z8 is abelian. Like, this doesn't really merit checking because, order in the group as a whole doesn't matter. And, we'll prove this rigorously, and, it's really just like one line here in a second. But first, let's look at 5, 7, sorry. So the group Z plus, and then your subgroup 3Z. What distinct cosets did you get here? Can you, name them? Did you notice a pattern happening? Because obviously, if you listed them all and didn't think about which ones were distinct, you would be listing them forever, right? You have infinitely many cosets here, but you should get a lot of repeats. So what did you notice? Yep, those are 2. Is there anything else? And 3z itself, yeah, or 0 plus 3z, yeah, exactly. So we should notice 3 things, right? So you have 3z, which is 0 plus 3z, because obviously adding 0 does nothing. These are all of our multiples of 3, right? And you go on. Then you have 1 plus 3z, which, same stuff, but we've added 1, so -2, 1, 4, 7, and so on. 2 plus 3z. And then once you hit 3 plus 3z, well, 3 is a multiple of 3, right? So I just get this same list back, because it went on forever in each direction. And so this is equal to just 3z itself. And so you notice a repeat. And so this is a little highlight. I mean, all of these you can turn into, well, the abelian ones at least, and the Q8 one that we saw earlier. You can create a new kind of group out of this, because what does this behave a lot like? Like these cosets. You see it repeating every 3. What does that remind you of? Does it remind you of any group you've seen thus far? Should feel somewhat familiar, even if the elements look different. Yeah, I mean, it reminds you of modular arithmetic. So this feels like, so, yeah. So if you have just this set of cosets, these 3 guys, right? This behaves just like R3 or Z3, you know, however you want to think of the cyclic group of order 3. So is this true? Yes, it turns out this is true, and like this is something we'll see later, so don't worry about the notation right now. So I'll just say, you know, later we'll see that this group called Z mod 3Z, and this basically does mean just like the cosets of 3Z and Z. So it's exactly this set above. This would be notated like this, or denoted, I guess is a better word. And this happens to be isomorphic to Z3. And this is something we'll see kind of toward the end of the semester. So yeah, it feels like that, and it turns out that they really are isomorphic. We just need to figure out how to actually talk about cosets being a group, right? And so that's something we'll do in the next chapter, okay? Those are called quotient groups. Okay. So we've noticed the pattern, right? This was also abelian, so like things didn't matter, right? If I add 1 on the right side instead of the left side, like I don't care, right? It's addition. I add on the left or the right, I get the same thing. And so this is true in general if H is a subgroup of G and G is abelian, then the left cosets are always equal to the right cosets. So when I was looking through some of these that were turned in kind of early this morning, I noticed one kind of common mistake, or it's not even a mistake necessarily, because it's something that's true, but it's just something that you don't need. So a lot of people noted that since H is a subgroup of G and G is abelian, the H is abelian. But we don't actually need the H is abelian at all here, right? Because A here may not lie in H. And so really all you need is that G is abelian. We don't really need to further state that H is abelian. And so since G is abelian, AH is equal to HA for all H and H. And the set of all A times little h over all H and H is exactly A times big H, right? And the same thing here with big H times A. And so thus AH is equal to HA. So it's really very quick. But notice, right, we didn't need that H itself was abelian. So the next thing that we want to do is figure out like why, so some things that we've kind of noticed, right, that like these cosets seem to have the same order, and it seems like, well, we would hope that like every element seems to lie in some coset, right? Like in all these cases we got like the whole group out of it. So we kind of want to work toward proving these things. So what it suffices to show is that being in the same coset is an equivalence relation, right? Because we noticed we had like several representatives, right? We could have taken 0 plus 3z, 3 plus 3z, any multiple of 3 plus 3z would give us the same coset. And so it'd be nice to know, like, okay, I only need to take one. Is there like some better way I can represent this? And the answer is yes. It's just an equivalence class of one element, and you could basically choose any of the elements in that class. They'd all be related, and so it suffices to just kind of like mention one. And also having equivalence classes means you're going to partition your group as well, because that's something we talked about, right? We had that picture way back where we're just like all our equivalence classes kind of do this to your group, and they partition it into pieces. Like they don't intersect one another, and they union to give you the whole group. And this is very important for proving Lagrange's theorem. Okay, so this is kind of working toward showing that every subgroup has an order that divides the order of the whole group. So first we just have to define this, and I guess, you know, it's stated as a theorem, but it's something we've actually already proved in a problem set. And so that is, if we have H as a subgroup of G, then we say A is related, you know, L related or left related to B, if and only if A inverse B is in H. And you can do the same thing with the right, except here it's going to be A B inverse is in H. And so if you just like look at this, it's not clear maybe where the left and right are coming from or how this relates to cosets. And so that shows up in the next thing. So first, the conclusion of this theorem is that, I guess not this, these are both equivalence relations on G. Right, so again, that was something you showed on a problem set, so I don't think we necessarily need to go through it here. But to kind of say why they're written like this, it's because this kind of has a correspondence to left cosets, and this has a correspondence to right cosets. Right, and so that was exactly theorem 510. So the statement here is basically about equivalence classes, right? So remember that an equivalence class with a relation is just everything that's related to it, right? So this is going to be the B and G such that A is left equivalent to B. Right, so that's just the definition, and again, you'd get the same thing with the right. We will usually use left cosets just by convention. And obviously, all these proofs basically would be the same. If you can do it for the left, like the argument is going to be very, very similar for the right. And so 510 is the statement relating these two things to cosets, right? So again, H is some subgroup of G. We have our equivalence relation. Then AH is equal to the set of equivalence classes under the left relation, and the right coset is equal to the set of equivalence class, or sorry, the equivalence class of A under the right relation, just a single equivalence class. Okay. So we're just going to focus on one. We'll just prove this guy, again, because they're basically the same argument. So what's the key here? I mean, you have to show both directions, right? We want that each is a subset of the other. But in this case, you can really do it with all if and only if statements, because it really just breaks down from the definition, okay? So the way I usually think of this is, okay, what does an element look like right? So can I say basically an element lies in this left if and only if the element lies in the right? So I just take some arbitrary guy and I'm going to see what happens, right? So x is in AH. Well, what does this mean? Well, it means that it is of the form A times some little h for some little h in H. Right? That's just by definition what that left coset means. Okay. Well, how do I relate this to my left relation, right? So, well, I know I need to get towards the A inverse B kind of thing, right? And so in this case, well, I need like the A inverse. So I'm just going to move this over. So this is true if and only if A inverse X is equal to little h. But this is exactly the statement of, well, I'll do one more step. So this would be the same as saying A inverse X is in H, right? We've written it as some element of H. And now this is exactly the statement about the left relation, right? So this is true if and only if A is left related to X. But if A is left related to X, that is exactly the definition of X being in the equivalence class of A. And then, you know, HA equals this is similar. Okay, so that was a lot of talking there. Hopefully each step makes sense, but are there any questions on what we just proved, or anything so far? Okay. Alrighty. So this is where, you know, I didn't necessarily have you prove the corollaries, mostly because they really do follow immediately, but it is important that you read them and understand like why we prove what we proved, right? So the key thing that follows from this, so all right, this is a corollary to 510, so it follows immediately. We know in general that equivalence classes partition our set. So that means that the equivalence classes under this relation will partition G. And so from 510, we know the AH, this set, will partition G. And so what does this really mean? Well, is A in H and G, or is it just in G? It's in G. Yeah, it's just in G. It could be in H, but it does not have to be in H. How do we know A inverse exists? Yeah, exactly. Mansell is right. Yeah, it's a group. I don't think it's relevant if it is in H. It's relevant only in the fact that it tells you it's the coset H itself. But otherwise, yeah, like it's not relevant for general statements or proofs. But we'll see here in 514 that if A is in H, like that is the only case in which the coset AH equals just the subgroup H itself. Yeah. So again, if you, I drew the picture above, but like notationally, what does this mean to partition? So what this means is G can be written as a union of the distinct cosets. So we'll just say the distinct cosets down here, and the fact that it's a partition means that these guys do not share any elements. So AH intersect BH equals the empty set if AH is not equal to BH. So basically, if they're different cosets, then they do not share a single element. If they do share an element, they would have to be the same. Right, so think about all your examples above, right? So you had something like 1, I, and minus 1, and then you had, j minus j, k minus k, right? Like these had no overlap, and they became our whole group. So it's like the union of these two distinct cosets, which share no elements. So like this always happens with our left cosets, and that's what follows from 510. So that's what I mean by a partition. Let me know if that doesn't make sense, and I can maybe talk more about it. But that's the key. I can always write this as a union of these distinct cosets that do not intersect one another. So keep this in mind for when we're proving Lagrange's theorem. That's one of the very key ingredients. Okay. And so the next thing that you guys had to prove, and this looked pretty good in general from what I was seeing. And again, this is something we've noticed, right? So this theorem should not have come as a surprise. You've noticed that like these cosets always have the same number of elements, right? No matter what. And we want to prove that this is just always true. And so we want to show that the cardinality of H is the cardinality of AH for any A and G. So basically, any coset is going to have the same number of elements as the subgroup H does. And the way to show that is that you can literally just pair them off. So if you can show a bijection or a one-to-one and onto function between these two sets, then you're good. And this is a map that you could probably think up on your own, right? Like if I want to go from H to AH, well, what's the difference? I've just taken things over here and I've left multiplied them by A. Well, that's going to be exactly your map, right? So we just define V of H to be AH. And then our goal is to show this really is one-to-one and onto. So for one-to-one, right, we want to assume that two things are mapped to the same thing, and then show that those two things must have been equal to begin with, right? So suppose, we're taking things in H, so suppose, say, H1 and H2 lie in H, and phi of H1 equals phi of H2. Well, then we just directly translate this, right? This means AH1 equals AH2, and we can just cancel these guys out, right? Multiply by the inverse, and we get H1 equals H2. So we're one-to-one. That one's not bad. Phi is also onto, right? So here you want to start with the general thing in AH, right? So let's say Y be in AH. We need to find what maps to it, right? So there are a couple of ways to do this, but I think the easiest one is just to say, well, if Y is in AH, then Y is equal to A times some little h, right? For some little h in H. Well, this is exactly of the form phi of H, right? We left multiplied our little h by A. And so this is exactly phi of H. So phi is onto. We found the thing that mapped to this guy. Another way to do this is to note that phi of A inverse Y is equal to Y. And again, Y is in AH, right, because we just left multiply by A, and so A and A inverse cancel each other. Y is in AH, so A inverse Y is in A inverse AH, which is equal to H. Right, so like you can view it either way. You know, this one maybe feels a little more general. I never had to really talk about a little element in H, but I think like they're the same, essentially, right? So I think either way is fine. Okay. Any questions on that one? No, for onto, onto is for anything in the codomain, then there is something that maps to it via phi. So we wouldn't know in general that, I mean, in this case, yes, a phi inverse does exist, but in general, a map can be onto without an inverse existing. So we wouldn't necessarily even be able to talk about phi inverse. You could talk about the pre-image being non-empty. That would be another way to think of it, though. Okay. So the key corollary here, right, is basically what I stated right before this in terms of what our goal was that we wanted to show, right, this. And so that is what we get immediately. If there's a bijection between the two, then they have the same cardinality, right? We can just pair them off one by one together, and that gives us the same cardinality. So the corollary is that this is true. And again, like you could have just done right multiplication instead of left multiplication, and so I'll just put in parentheses is also equal to the cardinality of HA. So like whatever I have been saying for left cosets also works for right cosets. You just have to like make a slight adaptation to your argument for any A and G. All right. And now we are pretty much done. We just need to verify a couple more things before we're ready to prove the theorem. And that's basically that we know exactly that every element lies in some coset, and exactly which coset that is, and then we're pretty much there, okay? But in this, we're also going to gather like a couple more facts. I guess technically we could just do Lagrange just from here, but we're just going to gather some facts in general about cosets before we prove Lagrange's theorem. So that's what this 514 is. So these are going to be useful like down the line if you're trying to prove things with cosets. These are good things to remember. So same situation as always. You just start with some subgroup, and then we can make a whole bunch of claims. Okay, so I guess I wrote that as A, B, C, and D. So if you have some element in your group, then it lies in some coset. So again, this also follows from the partition thing above, but it's nice to know exactly which coset it lies in, and it lies in the one you think. It lies in AH. And again, same thing would be true for right cosets, that it lies in HA. So, you know, proof here is not very hard, right? Can you think of how you can write this? So how do we know that little a lies in little a times big H? How can we show this? Can you write it as a product of A and something in H? So to be an AH, right, that means you can write A as A times little h, where h is an h. Yeah, AE, exactly. Yeah, so not, right, A is not necessarily equal to A squared, and like closure, I mean, yeah, it doesn't necessarily apply in terms of telling you like what to multiply by. The key here, right, is, I mean, you could back solve here, right? You could just multiply by A inverse and see that H has to be E, and that's exactly the idea. So A is equal to A times E, H is a subgroup, so E is in H, right? We know this. Yeah, E is in H since H is a subgroup. Cool. So we have A in some coset, and we know now exactly which one. Another issue that we've kind of run into, right, is like these cosets seem like they could be represented by a bunch of different elements, right? Like I had earlier that, you know, I times this equals negative I times this equals 1 times this equals negative 1 times this. Like, well, which one do I use? Well, the point is you could use any of them. And so this is what we'll kind of like get a result on here. So B is in AH if and only if AH equals BH. Okay, so basically they're the same coset if and only if one is an element of, like the little b, the representative itself, is an element of the other coset, right? Because we already know b is in BH from part A. So one way is very easy, right? This way is very easy. If AH equals BH, well, then we know B is in BH from A, so B is in AH since BH equals AH, right? So that one's pretty much immediate. So what about the other way? Well, we can start with this, right? So B is in AH. So what does this mean, right? So our goal is to show, again, that like AH, a general thing in there, lies inside BH, and that a general thing in BH lies inside AH. But you can do this in like a little a little easier way. So what would be easier is to say, okay, what is AH? Well, or sorry, so this guy, B is equal to A times some little h, right? Okay. Well, I should be able to just kind of substitute. So now if I think about BH, like the coset, well, this is equal to AH, but I have closure here, right? So HH, this is going to be equal to H. Is it clear why that should be true? So I mean, it's clear why it should lie inside it, right? Because of closure. Why is it actually equal to it? So I guess, you know, why? Why is this true? So we know this is a subset by closure. And then the reason it's actually equal is, right, H is a subset of HH2 because, well, you can think of it many ways, but basically inversion is allowed, right? So because left multiplication by h is a bijection, right? It's invertible, right? We can invert it by multiplying by h inverse. We already know that left multiplication is an isomorphism in general. This is what was like the key to Cayley's theorem. And basically, right, so like h times some other element in h is always going to be an h. That's closure. And you can never go to two of the same things, right? Because like if you have hx equals hy, well then x must have been y. So it's 1 to 1. So you're always going to two different things, and you're going to thus hit everything. You've just done some permutation of the things in h. Okay? And so once you know that, then what we've written is BH equals AHH, which is equal to AH, since HH equals H. So that's kind of a little faster way to do it, which basically involved proving part C. I mean, that basically was part C, the HH being H part. I think that's actually easier than doing like some sort of substitution. Essentially, you could have done that as well. It's just a little longer route, I think. So C is basically what we just said. So if A is in H, then AH equals H. And again, would also equal HA. So left multiplying by an element in H just permutes the elements of H. Okay. And then the last one, which also should make sense, is that if A is not an element of H, then basically there is no intersection. So little AH is not in H. So anytime you see like a not statement like that, it should be somewhat natural to think of contradiction. Okay, so like what if it was, right? Like if you want to prove this, like suppose AH is in H. Well, then AH equals some little H prime, say, with H prime in H. But then you have inverses and closure because H is a subgroup. So A is equal to H prime H inverse in H. But now we have a contradiction, right? A is in H, but we said A was not in H. So this is a contradiction. And thus, AH must not have been H. And that's basically how you see the, if you don't want to just think of equivalence classes giving you this big hammer to show that these guys don't intersect one another, this is the way you could do it kind of in a longer, more elementary method. Okay? All right. So now we're ready for Lagrange's theorem. That's what we'll kind of close things with. Okay, so the statement, now this is going to be for let G be a finite group. Otherwise, we don't really care about divisibility because dividing into infinity is a weird thing to do. So we're only going to consider a finite group. And again, H will be a subgroup. Then the order of H divides the order of G. And specifically, that quotient is equal to what's called the index. And so I'll define this here, where you just write this like G colon H, where this is like your group, this is your subgroup, is the number of left cosets of H in G. And it's called the index. of H and G. Okay, so basically what we should get is that we have the order of G divided by the order of H is the number of left cosets. Okay, so our pieces are exactly 511 and 513. We use primarily 511 and 513. Because what we're going to do, right, we know it partitions the left cosets. So we know the left cosets partition G. So here just assume we have some finite number, right? So since G is finite, it has finitely many distinct cosets. And so we'll just list them. Let's just say, we've got A1H, which is equal to H, so you may as well take A1 to be the identity. A2H down to ANH. And so in this case, right, N would be the index, because that's how many distinct left cosets we have. Okay, so we've got a finite group. We've got cosets that cover it. There have to be finitely many of them because it's a finite group. And they all at least contain some element. And so we know it partitions. So since these partition G, G is equal to the union of them. So it's like A1H union A2H down to ANH, where AIH intersect AJH is the empty set if I is not equal to J. Basically, if you take two different cosets here, right, then they do not intersect each other. So this is exactly the statement of partitioning. Okay, well, then what can we say about the order of G? Well, these guys union up to give you G, and none of them share the same element. So if you just add up the number in each of them, and then add up those, you get everything in G, and you never double counted because they don't intersect. So this is just the cardinality of A1H plus the cardinality of A2H down to this, since they don't intersect. Right, so we never double count. Well, what did we show in 513? We got that all of these guys have the same cardinality, which is the cardinality of H, right? They all have the same number of elements in these left cosets. Thus, I'm really just adding up the cardinality of H every time. So I get order of G is N times the order of H, because I get exactly N things here, right? So it's basically N copies of H. They're just like different elements. Well, that's exactly the statement of divisibility, right? So order of H divides the order of G, and order of G over the order of H is exactly N, which I said was indeed my index. And so there we go. So this is a huge result. So we kind of broke it into pieces there, right, earlier in this chapter. And so we were primarily using these two results that we already had. But this is a really important one. It's been on comps a lot, so it's important in terms of just like practical things for you if you are a math major. But it's also going to be super important for us in class and in general in group theory. I mean, this is one of the most powerful theorems in the entire field. Okay. So we're pretty much out of time. Are there any questions on this? If it's a longer question, I mean, I can hang around in Discord for a little bit after, before I break for lunch. But I can answer something quick here if you have it. All right. Well, if there are no questions, then I will be around, like I said, for a little bit, and then I'll be around this afternoon as well if you have questions during office hours. Okay. Have a delightful day.